Let's learn about this very important concept of visibility problem. Before we start learning about the visibility problem, let's take an important detour to understand and visualize how cores, registers, and caches are placed along with the RAM. The image here is showing a machine which has 6 cores. On the first layer, we have the cores. Cores are the piece of hardware which are responsible for all the compute activity. Loosely speaking, core itself does not have any storage capability. It can only compute. But in order for the computation to happen, we need to have some sort of data storage as well, right? This is where we have different type of storage units. Let's know about them in a very brief manner. First on the list is a register. Every core has a dedicated storage component which holds the data temporarily during the execution of the instructions. This storage component is known as register. It has the least amount of storage capacity. Each core has a dedicated register. The next one in the line is the component of L1 cache. L1 cache is a small but a very fast memory. It plays a crucial role in improving the performance of the CPU by reducing the data access time to and from the main memory, which is also known as the RAM. Each core has a dedicated L1 cache. The next component is the L2 cache. It is a larger capacity cache as compared to the L1 cache. Its role is to complement the smaller and faster L1 cache. It does so by providing additional storage for frequently accessed data and instructions. L2 cache is integrated in two ways depending on the architecture of the processor. In one approach, the L2 cache is shared across different cores, whereas in the other approach, we could have dedicated L2 cache for a core. The presentation that we have here, we are showing a shared L2 cache, where the cache is being shared by two cores. For example, here core 1 and core 2 are sharing this L2 cache. Likewise, core 3 and core 4 are sharing this particular L2 cache, and so on and so forth. The third type of the cache is L3 cache. It sits between the L2 cache and the RAM, which is also known as the main memory. Its role is to provide a larger pool of cached data and instructions which can be shared among multiple CPU cores. The final type of a storage layer is RAM, and as told earlier that this is also known as the main memory. It serves as a temporary storage for data and instructions that are actively being used by the CPU. So on the one end of the spectrum, registers store the data specific to a core, and on the other end of the spectrum, we have RAM, which stores data and instructions being worked upon by all the cores of the CPU. When we go farther from the core towards the RAM, the latency and memory size increases. So RAM would be of larger size as compared to L3 cache. L3 cache would be of larger size as compared to L2 cache, and likewise register is the one which has the least amount of storage capacity. But since register is closer to the core as compared to the L1 cache and L2 cache, register would be faster, in fact the fastest type of memory, whereas RAM is the most farthest one from the core, so it is the slowest of the lot. So the RAM would be the slowest memory and the register would be the fastest memory. Let's see this diagram. What we have here is a code snippet, and basically we have two methods. Assume this write method is being used by a writer thread and this read method is being used by a reader thread. And this particular code snippet is being executed in this kind of a machine, wherein we have two cores, and core 1 is executing thread 1 and core 2 is executing thread 2. So to begin with, there is a variable whose value is 0. The count variable starts with value 0, and assume at certain point of time thread 1 gets to execute on core 1 and thread 2 gets to execute on core 2. So basically both of these two threads are running in parallel. So the value of count is updated as 1 by the writer thread, and at the same time the value count is loaded in the value. So what would happen if you try to access the value of val by either printing it or debugging it? So you may see something like this. So to begin with, count is 0, that is in the shared cache. Then the count is updated to value 1 and this value is there in the register which is local to core 1. Now core 2 is running thread 2 and it is trying to access the value for count. So remember that as of now the value of count is 1 is only with this register. It has not percolated to the shared cache level. So the value that is present for this count variable is still 0. So the value that is assigned to val is still 0 in this register. And when we try to print this value, we will get the value as 0 as opposed to what we were expecting, which should have been 1. So this is not something which is expected and correct, right? So this kind of behavior is called as the visibility problem. Java provides a solution for this with a keyword called as volatile. Using this keyword ensures two things. First is, whenever there is a change in the value, it's flushed to the shared memory. Second is, whenever there is a value which is supposed to be read, it's read from the shared memory. The shared memory is usually, and in most of the cases, L3 cache, which we saw earlier to be the shared cache, and this one is a level up to the RAM. So basically what I'm trying to say is, let's say if I used volatile with this variable, so what I'll do is I will write this as volatile keyword then int count, right? And then when thread 1 is executed and any value to this variable is changed, it won't be only there with the register, rather it will be written to the shared cache as well. And since this variable has been made volatile, the thread won't read this value from the register or any other cache, rather it will directly read from the shared cache. So on the right, we are ensuring that the value for the particular variable which has been made volatile is going to the shared cache, and for the read as well, we are ensuring that value is read from the shared cache itself. So that would avoid us in reading wrong value. And this is how the volatile keyword helps us with the visibility problem. There is a word of caution we should always follow while making use of the volatile keyword, however. While volatile does help with the visibility problem, as a side effect, it slows down the code and thus the application. It's a no-brainer that with the uses of volatile, the many layers of caching are removed, and so are the latency optimization benefits which we gain when we use the caching. So when not needed, the uses of volatile keyword should be strictly avoided.